So as I said, this is inspired by Haruki Murakami's book cover called What I Talk About When I Talk About Running. And I guess I could have called What I Talk About When I Talk About Running on multi-platforms, on multiple platforms. But I felt it was okay to do this homage because he actually stole the title from Raymond Carver's book, which is called What I Talk About When I Talk About Love. But that's a totally different subject. So my name is Adi. I'm a software architect. I do a lot of computer vision, machine learning. I target a lot of platforms with the products I work on. I'm also the founder of the Core C++ users group in Israel. So we have a conference in May. Talk to me if you want to join. And I think the first question that comes to mind is what I mean when I say cross-platform. Because these days, a project can actually target multiple different things that we might call platforms, and we can think about them in multiple different layers. So maybe at the lowest level, we have in some kind of custom board, a custom chip made for your own company, for other companies. We can think about embedded systems that use off-the-shelf embedded real-time maybe controllers or microprocessors. Of course, we can have the same product targeting a mobile. Even a product that targets only mobile devices might have to, or would generally be expected to target both iOS and Android, and if some other player wants to come in, we might need to consider that. Of course, on desktop, the leading operating systems, we have Windows, Linux, OS X. And today, the web is totally a platform that we must think about, we must consider. And I've written software that had to target browsers 10 years ago. And back then, we had to write ActiveX controls for Internet Explorers. There was a whole technology based on plugins, browser plugins. Google tried something called the native client. And these days, the de facto standard is JavaScript, but also WebAssembly, which really allows us to compile C++ code for the web. And we'll actually see some examples of many of these a bit later. But that's not all, because sometimes our software needs to run in the cloud. And over there, we already have server racks, we have Docker images, we have Node.js, serverless, and many, many more. And more platforms are coming online every day. So our vehicles are becoming smarter, and we might have to have our own software running inside the vehicle. We have robots, we have GPUs and CPUs, heterogeneous computing, we have IoT devices. And my basic premise is that C and C++ are probably the only viable languages for true cross-platform development. I hope I'll be able to convince you. This is not the main target of the talk to convince you, but more about to show you how we might be able to manage our software systems in such a way. Now, I'm not going to talk about frameworks, because that's a totally different subject. The things we're going to discuss are maybe whoever writes this framework, the aspects that the people who write these frameworks or these JVMs, they have to think about when they're building their own project. Now, when you go and read some popular websites, maybe Code Project, MSDN, I just got some Qt code yesterday that I was looking at, and usually they mix a lot of concerns of the platform-specific part or the specific APIs with actual logic data. So you get something which is very difficult to refactor, very difficult to maintain. It's very often it's not portable. So even if you're using Qt, it might not be portable to the embedded device you're working on or to the particular cloud architecture you're targeting. It's very difficult to test. And there's another aspect that we might not consider every day. It very often has a mixing of skills. So the people who are iOS developers won't necessarily be able to debug algorithmic code, and the same way the people who are doing Android or JavaScript development might not be the right people to maintain your algorithm, some other part of the system. So, and if we're talking about module boundaries, we need to understand how errors propagate inside our systems. And all of these are aspects that really get mixed when you go and read some more expository code online, which mixes a lot of these SDKs together. So remember Code Project? Has anyone here ever come across this type of mixing of SDKs and problems when just looking for some algorithm code? Yeah? Yes? See some heads nodding. So this is where spaghetti code comes from. Now, over the years, I've developed the kind of methodology that's kind of born of frustration. It's because I had to develop all these systems that had to target multiple platforms, and I came up with, I call it the Salami Method. You'll see I didn't invent much here, because I think it's like most design patterns, it's been discovered and rediscovered frequently by many different people in many different places. I just chose to give them some really bad acronym names so we can not remember. Okay, but basically the idea is that we could more easily build and test, debug our system, manage and maintain them, such that we can get the full effect of our code and our team. Now, this is not a magic solution. So if you've done any cross-platform or platform-specific code, there's often very ugly cross-platform boundaries that you need to handle, but at least we're going to keep it cornered in one part of the system and not have it encroaching on the rest of the architecture. Now, I will say, if you have any questions, please ask me while I'm talking. It's easier, and I'll try to answer. Right, so what we're going to do is basically we're going to slice the problem into extremely thin strips, thin layers, each one concerned with different aspects of building a multiple platform or cross-platform system. So, of course, the first thing is the well-known dry principle that don't repeat yourself. We want to avoid duplication and avoid re-implementation. I've come to work with teams who had a mobile product. They had one iOS developer team and another Android developer team, and they were basically chasing each other's bugs or trying to keep up with the versions, because these guys were developing in Java and these guys were developing in Objective-C. And we would like to, at least the program logic, the UI might be, is generally something that we want to keep to the front end, but all the logic behind it, we would like to be unified. Of course, single responsibility, testability, this all leads to transparency. It means that the code is easy to follow, the code is easy to debug, the code is easy to, and it's easy to identify places where something went wrong, and once it gets corrected, it can percolate down to the rest of the systems. As I said, that's when the business logic is isolated and shared, this is a huge win for all of our teams. Of course, if Microsoft finally does make some kind of mobile operating system that works, then we are already ready, right? Because the only thing we have to do is really write the application, write some of the UI code, the rest just works. I mentioned developer skills. Again, this is extremely important because we might have the world's best Android developer or iOS developer or maybe JavaScript developer. By definition, that person is not an algorithm expert because this is not what they do, and we want to separate those concerns. And of course, refactoring, again, when we have separation of concerns, it's easier to identify places where things need to be checked and changed. Now, this slide is really the gist of my talk, and basically we're going to look at all of these layers. We have multiple layers here, and on the right I'm going to mention aspects related to testing these layers, and at the bottom we have our cross-platform C++ code, and on top of that we're going to build and we're going to cross certain boundaries which are really important. And the important thing here is that we're going to talk about concerns when writing cross-platform code. So, and these concerns occur in every project that has to do this. Now, very frequently, we're not going to have to implement each of these layers as separate parts of the code. Sometimes these layers can get merged into what I call thicker layers, but conceptually, these issues are still there, and we can never ignore them. So we're going to go back to this and see examples of each of these layers in a minute. But I think it's important to realize that all of these aspects always remain, and if you've ever done any such development in the past, you'll immediately identify them. Now, of course, at the heart of our system lies our cross-platform C++ code. This is our this is where the business logic, the algorithms, this is the proprietary code where we do the idiomatic C++. This is what most of the other conference talks talk about. How to design your system, how to use C++ more effectively, how to make it more performant, how to improve your architectures. Now this code obviously needs to compile on all your target platforms. But as I said, C and C++ are basically I don't think any vendor creates a silicon today that doesn't come with a C compiler, at least a C compiler, if not a C++ compiler. So if there is any language that can target most platforms, it's C and C++. And generally, we would try to link this core into some kind of static library, and this is where we can do a lot of unit testing, functional testing, and the focus really is, like many other talks here, is on solid code, maintainable, well-designed architectures, design patterns that are suitable for maintaining such architectures, and not so much thinking about underlying externalizing the code. Now, we can see on the top right here, this is the diagram we saw before. It's not meant to be readable, but we can see the arrow pointing at the lowest level. This is the core. And now we're going to start climbing up into the topmost layer. The topmost layer is the host app. So this is what the client actually interacts with. Now, on top of the core C++ layer, there's another layer which is actually took me quite a while to understand that it actually exists, and it's what I call the cross-platform public C++ interface. Now, this is the API that our customers, our users of the service, the users of the algorithm are going to interact with. Very often, it's exactly the same interface as your own architecture, but sometimes it isn't. Sometimes we might want to replace some of the more proprietary code and libraries or dependencies with simpler types. I've had code that used boost shared pointer, and the users didn't want to link, or they used some kind of boost service, and we had to change the API so they don't need to link with boost. This is a great place to think about initialization and shutdown. How does a user of our service initialize it, and how do you take care of object lifetimes? Is there one global singleton? Are we using OPEC pointers? Are we doing sessions? How do we do serialization, configuration? All of these aspects, which are not generally directly mapped to the underlying architecture, but should be exposed. So this is kind of a facade, a C++ facade, still totally cross-platform. But again, the focus here is on the service consumers. And the fact that we can separate this, I think Kate mentioned this in her talk this morning, that we have to think about the domain, the terminology in the domain of the user. So we might, in our own architecture, we might call it save and load, but maybe the client wants to call it store and restore or whatever. So this is a great place to also change the terminology for the particular service we're exporting and use some of the more specific terminology. This is a classic place to put C++ modules. We still don't have modules, but hopefully we should be getting them soon, maybe in C++ 20. So these are exactly the type of functions that we would expose publicly with modules. And generally, I'm giving here some tips on naming files just for us to have, of course, you can give whatever names you want. So let's say I had some core CPP file, then I would have a core _ API CPP file, and of course the H. And as I said before, this isn't necessarily something you'll have in all projects, because often the underlying system is simple enough and that's all it needs to do is export this particular service. But it's still an aspect that we must think about. Now we're going one layer up, and we're just going to cross the first boundary, and this is the no business logic boundary. So from this point onward, we're not going to change anything about the business logic, the underlying algorithms, the way the code behaves. And the main reason is that some target platforms are not actually going to be using any additional layers. Because since we were using C++, things like iOS or Objective-C, or maybe Emscripten, PyBind 11, all of these systems might not require, they can natively build C++ code and interact with it. So we cannot have additional business logic in layers above the one we're at right now, because some of our target system might not get this business logic. and then we'll have a kind of a bifurcation of logic, and this would lead us to our spaghetti hell, right? And of course, we don't want business logic because, as I said before, we don't want to duplicate code and get inconsistent behavior. So our third layer, which it's kind of hard to see here, but it doesn't actually reach all the way to the end because some systems might directly touch the C++ layer, but very often we want to do a C or a C-like API, to give a C-like API to our nice, beautiful C++ architecture. And the reason is that, you know, sorry, this is the public C interface. Yes, so this is a very very thin C API. And generally, we're using extern C for linking API. You know, because C is the lingua franca of computing, right? As I said before, no vendor is ever going to sell a chip without the C compiler. And this is a great place to do type conversions. This is where we generally have to do that. So if we add a function that expects a std string, at this point, we have to lower the type system to something that C understands, and we might use char star. And we have to think about how we manage object lifetimes via C interfaces. So sometimes we can use, I mentioned this before, we can use singletons, or we can use opaque handles. This is kind of outside the scope of this talk, but these are the general techniques that are often used. And things like function overloading need renaming. And at this point, we can do some mock and unit testing, but we're actually testing the C API. We're not testing the underlying functionality. One of the tips I have when writing this type of code is that in the actual implementations of the function, we're going to immediately be lifting all these primitive types to higher level types. So if we're expecting a char star, an array of characters, and maybe a size or an expected size, then inside our functions, we can immediately put them inside a std span or std string view in such a way that when we're actually manipulating these inputs within our own implementation, which is generally very thin, and we'll see some examples in a minute, we don't have to take care of, we can reduce the abstraction cost. We're lifting our types, we're using higher abstractions, lower bug, less prone to bugs. So let's see an example, so I'm not just waving hands here. So this is our header file, maybe for the C API, what I call the XCAPI. I warned you, I have some really bad acronyms. So we can see we have 4 functions declared here, and 2 of them are actually an init function in the C++ code, but in C, you can't overload functions with the same name, so we have to give them different names. One of them expects a file name, the other one accepts some count variable. Process buffer expects a pointer and a size, and is ready some kind of a Boolean function. And when we see the extern C, this means that we're getting the C ABI. It means that it's much more stable for linking, and it means that we could link this library with different compilers, different compiler options across different binaries. Now, I like to think of these, the extern C, I like to think of it as air quotes, not just as a string, because sometimes what it means, it's just like it's a C-like function interface. So you can see here, I'm actually doing exactly what I said you shouldn't do, and this function is actually accepting a string. It's not accepting a char star, and I'll show why in a minute, because it really depends what we're actually going to do with these functions. So if we're exposing them we have to do a C interface, then this might not pass, but some other systems, this might be sufficient to use std string. But the important thing is to think about standalone functions, because this is one of the most common ways to expose cross-platform code to different platforms. So now this is the C++, this .cpp file or the .c file, or in this case, the .cpp file for that header file we just saw. You see, we're including the relevant headers. And in this case, I just have one object. It's a single global singleton called the session. And as you can see, the functions are totally trivial. So that's why what I said, it's a syn function. This one just called the session.init with the file name. Now, since the implementation is C++. It's not C. C++ has function overloads, and we can use init the same function, and so on. And in process buffer, I mentioned before, again, we're lifting this pointer and size to use std span for the buffers and pass that on to session process. Again, session process comes from our C++ public API, which is aware that it's going to be exposed to a user, so it might actually be expecting a span, right? So again, this is the focus on the users, the focus on consumers. We already designed it in such a way that it can accept a span. Of course, if we're using a global like that, but it needs a proper constructor, then we might use optional or unique PTR, or if you need to do more complex, not slide-worthy code, then you might use opaque pointers or some other alternative mechanisms. And as I said, this is a very good example where the underlying API, this process buffer, is actually designed to be used with span because it knows that it might be getting lower level, more primitive types. Right. So we're halfway there. And we already passed the business logic boundary before. And now we're at the cross-platform boundary. So up until now, we were working with a C compiler or a C++ compiler and targeting our basically all of our target platforms. But now we're actually going to move to writing, we're still in the C or C++ world, writing C and C++ code, but now we're moving from the cross-platform boundary. And we're moving into what I call the boundary interface layer. And this is where we're going to do data conversions and handle more platform-specific issues that are relevant for the platform we're targeting. So has anyone here done any cross-platform, trying to target C++ to different platforms? Yes, okay, almost all of you. Great. So I'm sure you know, each platform has some strange conventions, strange types. Sometimes the types do not map directly to C++ types. Sometimes we have different constraints on how the data is represented. There are different conventions, naming conventions. We see examples of this in a minute. And also another important thing, this is a great place to do to add logging logic. So, for example, if we're targeting, we can use a cross-platform logging library, and this is where we set the back end of the library to, let's say, the Android logger, right? So this is a great place to hook our logger. And this is where we need to think about module boundaries, because some of the things we're going to do is really writing DLLs. They might not, sometimes they are DLLs, or when I say DLL, I also mean shared objects for Linux systems. But sometimes they might be like Python modules, which are basically renamed DLLs. And what happens when an exception is thrown from a DLL? Do you know? It terminates. Okay, so this is the last boundary. This is why we have Juanpe here. And if an exception is thrown, we have to catch it. We make sure that the error is handled correctly. An interesting thing is how you test this part. And I have no idea. I think there's I have an open Stack Overflow question that's been there for like 6 years now, and with no answer. It's unclear because if you go and do, let's say, the JNI or NDK in Android, there is no emulation system that you can actually run to check that your code here does what you expect. Some systems you might have that, but this is it's an open question, and that's why we want to keep this part of our system as thin as possible, although this is probably where all the ugliness goes into, right? So it's a kind of, it's not an optimal condition. And in this case, I would generally call the file by using a Core C API DLL or Core C API JNI. And again, this is the part where we actually have to write multiple implementations for each one of our target platforms. So let's continue with our example. And in this case, we have a Windows DLL or a Linux header for the same functions we saw before. And the same 4 functions. And we can see that of course, we had to put them in an extern C. We have this DLL export predefined flag, which is basically exposes it as a DLL exported function or imported. It's this kind of macro, and you can get CMake to generate it for you for both Linux and Windows, which is very convenient. Also, we have the names of our function. Now we have to decorate them with an even longer kind of a namespace name, so we don't have DLL name collisions, right? Because init from count, we might have multiple DLLs declaring, or process buffer declaring the same type of function. And in this case, we want to give the sort of the namespace decoration into the function. And another example you can see here that I use the LPC str, which is what Windows, for example, uses for passing strings around. So at this layer, we are already allowed, and sometimes we must use the native platform-specific types and platform-specific idioms for what we're targeting. So let's see the C++, what the C++ version implementation file would look like. It looks like a lot of code, but it's actually, each function is just a single line. We can see the init from full session init from file name. There's automatic conversion from LPC str to std string. So we're just passing, returning the value from the global init from file name. Remember, this is our the public C API that we saw from the previous layer. Again, and we're just basically calling the same functions. Each line, each function is a single call. I think some scripting systems like Swig would basically generate this for you, right? Because there isn't a lot of logic happening here. You might see something kind of you might not know. You see, I'm actually using something called the function try block here. So the try is outside of the main body of the function, and the catch is outside the body of the function. I find that for things like DLLs or libraries that expose a large number of functions, it generally keeps the code much easier to read and very compact. We'll see it a little bit later with what we can do with it. So we can see these are extremely thin wrappers and almost boilerplate. Now, since we said we're talking about targeting multiple platforms, let's see another implementation that's targeting Android, for example. So in this case, we're actually including, this is the JNI header right here. We're including the Android logger, again, the RC API, and this is another header file that I wrote for JNI utils that gives us RAII on JVM services. So in this case, we can see that the function declaration is actually much more, it's longer, but these are JNI conventions. So JNI export is, we have to prefix that to the name. JBoolean now, this is the type that the JNI knows how to expose to Java as a Boolean. Now we have to prefix the Java underscore name to the function name. And our functions all need the first two argument types are something dictated by the JNI standard. So again, there's a lot of boilerplate code, but anyone who has ever written a JNI function must use this type of convention. But we're only limiting it to this tiny file, which keeps all the ugliness only here. And again, all the functions are a single call, except this one where I'm creating this RAI JNI byte array adapter, and I'm getting just accessing the data. Two more comments about this is, in this case as well, one of the things when we want uniform handling of exceptions. Remember, this is the DLL boundary. If we get a C++ exception, the program terminates. So we want some way to handle these exceptions, and for some reason, C++ exceptions are actually difficult to, we would have to write the same try-catch block in all of the functions just to make sure that everything behaves the same way. So in this case, I'm still using the function try block syntax, but I'm actually returning something called exception handler, which is, this comes from, I guess, the JNI utils. And this is a special function that will call throw again internally and do my the throw catch inside itself, convert that exception to a JNI exception. It would actually create a new JVM exception on the JVM, inject, let's say, the exception string into that exception, and then return normally from the DLL. So what we just did, we just translated the C++ exception into a Java Android exception inside the JVM. So this is one of the things we can do. And since we're using a function to do it, we can get uniform exception handling on all of our functions in our DLL. Questions? Cool. Right. So going up one more level, this is the native import layer. Okay, so now we're not in Kansas anymore. We just left the C or C++ world. We're running on the device now. It's a different hardware. It's a different operating system. It's a totally different language on each platform. Totally different conventions and idioms. And this is where we need to use what I call the native interface, because the word native is actually overloaded twice with opposite meanings. Because the native, let's say Objective-C is the native development language for or Swift for iOS, and they call the C code native, but actually it's kind of it's a very funny way to think about it, because sometimes you think about the C code as native to the architecture and not, or to the CPU and not the higher level languages. So this is where we're going to use the native interface that allows us to expose the DLLs inside the target boundary. The target language. We're going to reflect the boundary interface layer, and usually this is extremely low level and very, very direct, very boilerplate. Some system will generate this for you automatically. And the kind of testing we can do here is just simple integration tests, just making sure that our API from the Java side, or from the C# side, or from the Python side actually does what it's supposed to do. So you see the names are actually the extension. This is a Java file. We have a DLL, a C# file, or a JavaScript file. Because now we're already in the land of Oz, I guess. So let's see an example. The same system that we did. This is Java, but C# looks almost identical. We have a static system load library. Basically, this is how we load the DLL in Java. I'm not a Java developer, but apparently this is how you do it. And we can expose all of the DLL functions using this very specific API, public, static, native, Boolean. And of course, these types must match the underlying DLL prototypes, which are actually checked at runtime. And as you see, the types we're using here, they're Java types. So this is a string with a capital S. This is Java. This is not C++ code. And we're using a byte array and Boolean, which is the Java type. Now, as I said, this API may be very low level and very unnatural to the natives in the sense of the Java developers, right? So the people who develop for Android, they're used to Java, and working with arrays of bytes is not necessarily, maybe in certain cases, is not necessarily the most natural thing to do. And this brings us really to the last layer, which I call the native interface wrappers. And this is where we're creating higher level wrappers over the underlying low level DLL type APIs. So it's here, that we can give the user much more natural, much more familiar syntax that uses the idioms of that particular platform. So they feel more comfortable. Of course, this is, again, we can do target integration testing. And of course, the naming conventions are whatever you use on your platform. And we can see an example here. So I'm actually using a slightly different set of a different library just to show the point. So let's say I have some kind of DLL called native face detector. I'm loading it into Java, and exposing a function from the DL called getFaceCenterPoint. Now, the only way we can return two values, two floating point values from, let's say, from the DLL is an array of floats. But passing an array of floats to a Java developer to represent the XY coordinates kind of very low level, unintuitive, and error prone. So we might create another function. In this case, it's in the same class. So as I said, it's not necessarily separate classes. And I can call that getFaceCenterPoint with a capital G, which is more native to the Java developer. And this one returns a type called pointf from the Android graphics module and sets those points to this coordinate. So it uses center point 0 and center point 1 and just sets this point. And now the Java developer feels at home with this function with camel case, with starting with a capital letter and returning a type, a high-level type called pointf that they know how to work with. Now, you might think this is kind of esoteric, and it's indeed, I think it's the thinnest layer on top, or the narrowest one. But this is how all of the Android SDKs are implemented. All of the Android SDKs that are built upon the underlying Linux operating system, the system services, are built exactly this way. You have C code that will compile for Android, expose as DLLs, and some Java wrappers written on top of it with some higher level type abstractions covering it. So, and now we're actually ready to deliver this to our users for each group. So we can give a class to our iOS developers and our Android developers, our web developers, maybe our cloud developers, and each one is getting something that they feel at home with, they feel natural with, because we did all the hard work. But we managed our system in such a way that everything is under control. And sometimes different people we might have a team of maybe C++ developers that have touched different architectures, and they might be more familiar with the conventions, or we might work with some people from the other teams to get the right conventions. Right. So I like this slide because I think it shows kind of the path that we took. Here, it's the same diagram, but on its side, because I think that the y-axis here is abstraction and expressiveness and type safety. And very often, people who try to expose C++ code as C code or to write libraries, it's very easy to go down and create these C functions that have low-level primitive types. But it's very rare to see the expressiveness going back up on each target platform. And I think you can get this beautiful symmetry. And I have written systems that target many subsets of that list that we've seen before. And it makes for happy developers, and it makes for happy colleagues. And it allows you to very easily find bugs and problems in your code. So all of the things I showed you here are not hypothetical, they're not theoretical, they're more, and I think if anyone does have to target these platforms, I'm sure you've already done many of these steps, if not all of them. I've had people come to me after I've given this talk previously, and people come to me and say, yeah, this is exactly what we do. So I'm not even claiming to be inventing something here. I just put it in order, and I'm showing all of these aspects, because all of these aspects do exist in your systems. Now, how are we on time? 20 minutes, okay, good. So, as I said, we don't necessarily need to implement all of these layers all the time for all of our systems. Sometimes they could be unified into less classes, but they always exist. So we do have some more time, and I wanted to show you a quick example. So who here knows this animated GIF, the party parrot? Yeah, okay, some of you, like a third. Okay, so this animated GIF is actually made from a video about an extremely rare and endangered species of parrot. It's called the kakapo in New Zealand. And it's a clip from a BBC video. And this particular guy is actually called Sirocco. So I said, okay, I do a lot of computer vision, and I like to play with videos and color spaces and that kind of thing. I said, okay, maybe I can find the original video and try to do the same kind of transformation. But I wanted to do it on multiple platforms. So I wanted to see if I can do it to target both the desktop and the web. So create a web page, because this is a web meme, and I wanted to see how we're going to do that. So the first thing I did, really, I wrote a small program using OpenCV. OpenCV is the open source computer vision library. It gives us a lot of facilities for handling images. And I wrote a function called rotate hue. It takes an image, CV mat 3B means it's a 3-channel image, returns another 3-channel image, and takes some integer saying how fast we want the color to change in the frame. So we're going to be accepting frames from the video, converting the RGB color space to something called the HSV color space, basically changing the hues of the image, and then returning back the RGB image for display. So it's a single function. I'm not going to go into the algorithm because it's kind of beside the point, but it's a single C function. Clear all is another function that just frees up memory in case, because we're going to use some internally, it uses some globals to allow us to not have to reallocate every time the function is called. So note that this is all I need for my cross-platform C++ API. And this is already a C-like function, so this is already like the cross-platform C API, right? So I've already done, by implementing this function, this is already the lowest 2 layers that we've seen before. And since my API is just a single function, I don't need to create any higher, any extra public interface. So now we have to target the boundary interface layer. Remember, this layer is the layer that targets specific platforms. So when I compiled my program for on desktop, then I could, in Visual Studio, I could just compile my code and show it. But my other platform that I wanted to target was the web or the browser. So I want to run my OpenCV program, which is a C++ program, inside my web page. And Emscripten has anyone here heard about Emscripten? Okay, most of you. In case you haven't, Emscripten is a fork of LLVM and Clang, which can compile C++ code to a subset of JavaScript, or alternatively to something called WebAssembly, which can be run in your browser. So I'm actually going to run this real-time video color shifting algorithm, which I wrote in C++, as a sort of program in this strange subset of JavaScript inside the browser, in the client side. So I'm not talking about, there's no service here. With the server, everything loads on the client side, and the data is managed. So remember, the boundary interface layer is where we actually can include the platform-specific side. So we include the Emscripten header. We declare our extern C API. We need some special conventions for the functions declaration. And the thing is that browsers, since they come from JavaScript, they have their own conventions. So in fact, images in the DOM tree, and this is not strictly related to JavaScript as much as to the way that the DOM trees and HTML documents work, they only accept images are always defined as RGBA images. So we actually have to accept something called, it's a 4-channel image, and the channel order is actually RGB, red, green, blue, and alpha channel. Okay, and OpenCV, for various historical reasons, actually treats images as BGR. This is how it was in the old IBM systems back in the late 80s or something. So a lot of this code, and of course, this is a low-level C interface, so we have to define our image width, our image height are separate variables. We have a pointer here to some kind of memory to 4-byte pixels. And this is our output, and the number of steps is going to determine the speed that we're going to be changing our colors. And most of the code just wraps this pointer data. Like I said, we're going to be lifting. We want to lift our types as quickly as possible so that we don't have memory leaks, we don't have bugs. So we're going to wrap them inside OpenCV for channel images. We're going to create an RGB image. We're going to do some moving around of the channel, mixing the channels, running our function. So all of this is just to call our rotate hue function. But now it's getting actually the BGR images and returning a BGR image. Then it's going to remix the channels again for the DOM tree format and returning it. And once we can compile this, the output of this file is actually going to be a JavaScript file, a JS file, which is not human readable, or maybe it's a WebAssembly file, but it is browser readable. The browser can read it, and we need to serve it. Now, remember, the next layer is it's what we call the native import layer. This is already written in JavaScript. So this is a wall of JavaScript code just to show you my JavaScript skills, which are, this is most of the JavaScript I've ever written. All it does really is just hook into the HTML video and grab the frames, manage some of the buffers. And the really interesting part is our call to module is the name of the object, the global object that Mscripton generates, which gives us, exposes the function rotate colors, and we pass it the width, the height, the pointers to the data, and the color change speed variable, right? So again, this is, you don't really need to read this code, but basically what it does, it just, now we're in JavaScript world, and we're reading a JavaScript function, and we're passing it the data. And that's almost all there is to it, because the host app for the web, all it is an index HTML file, or it's just an HTML file, right? So in this case, we're setting a, we're loading our color cycle.js. This is the file we just wrote, which does the HTML video manipulation. We're loading our assembly file, which is what Mscripton built. And we were just writing some JavaScript to read the video, tell it where the video resides, and creating some kind of input widget to change the speed. Because we want to control how bad the party is, right? So how fast the beat of the music is. So this is basic JavaScript, and we're setting a controller. And let's see what it looks like. Yeah. So let me. Okay. So this is, if you don't recognize, this is called the Edge browser. On the left, we have our original video. This is just a regular HTML video tag. I just put the video tag, the name of the video, and that's what the browser shows. On the right, we're seeing the result of our C++ application. Running in real time, because we're hooking into the browser video play event, catching the frames, sending them to our function, calling our color conversions, rotating the hue, getting the result back, and showing it on the screen. And you can see that the video is playing almost at the same rate as the normal video playing on the left. And this is the little speed widget. So if I go, you can see if I move it to the left, so now the speed is 0, then it gets, the color on the right is exactly the same color. It doesn't change because the speed is 0. But if we can move it to the right, you can see the party is really getting on. So this is real-time C++ code running inside the browser. Okay, in real time, processing video. And the JavaScript code that I actually wrote was very, very boilerplate and very generic. So it's not related directly to the app I was working on. And hypothetically, you could use that for any image processing or video processing app you might want to write. Yeah, and you can actually read more about the Salami method and this particular app on my blog. These are the URLs. And yeah, I'll take some questions. Thank you.